Hello everyone. All of us study for the exams. Some of us try to understand the concepts, solve the examples given in the notes on their own, practice some more examples, etc. Some of us just memorize the things given in the notes without understanding them. Now, the thing is, how often does it happen that the questions in the exam have the exact same wordings as those given in the notes? Not very often, right? The same thing is happening with our linear regression model. Hero in training, but zero in validation. So when it sees the unseen or new data, it does not perform very well in providing the results, right? So this problem is called as overfitting, which we had seen in the previous video. Our model had fit very well to the training data, but then when a new unseen data was given to the model, it performed very badly. Okay, so in this video, we'll try to understand how this issue can be resolved using regularization. So keep watching. Overfitting. Let's say you have three data points and you fit a curve passing through all the three data points. That is an example of overfitting. Your curve, your model basically has overfit the training data. Because it passes through all the training points, obviously training error will be equal to 0. This is an extreme case of overfitting. Now, let's say I fit a linear regression model to the same data. Is this overfitting? Yes, it can be overfitting. Basically, overfitting due to linear regression model or any ML model for that matter accommodates noise and therefore it becomes too sensitive to small changes in X. Even small changes in X can cause large changes in Y. Now, continuing with the example that I had taken in the overfitting video, X is the temperature in degrees Celsius above the baseline of 27 degrees Celsius and Y is the cold coffee sales in 1000 rupees per day. And we want to find the relationship between X and Y, the independent variable being X and dependent variable being Y. Let's say this is the training data. Now pay attention to the third data point. The temperature is not much different. However, the sales are huge. So this is day 1, this is day 2, and on day 3 there was some event or some holiday or some festival. Therefore, the sales bumped up. So this third data point is going to cause us some problems. Now let's fit ordinary least squares. Why do we call it as least squares? Because we try to minimize the sum of squared errors. So least squares, linear regression line. This is the model. Y hat is equal to b naught plus b1x, where b naught and b1 are the parameters that we try to find out. So b1 is given by this formula. This is also called as the closed form formula for the coefficients or for the model parameters. How do we arrive at this? We basically use calculus. The objective function is sum of squared errors, as we'll see, and we try to use partial derivatives to find the minima, and we get this formula. I'll make a separate video explaining this derivation in detail. Right now, we are only interested in demonstrating the point of ridge regression. So first we'll see what is the validation error that we get without using ridge regression, using plain and simple ordinary least square linear regression. So I'm substituting all the values from the data that I have already been given over here from the scenario. I encourage you to pause the video and calculate all these values on your own, and then you can resume the video and verify the values of B1 and B0 that you get. So B1, which is the slope, is 12.84. It's a steep slope. And B0 is the intercept. I'm talking in terms of the slope intercept equation of line. So basically, when I write this in forms of the linear regression line, my linear regression line will be y hat is equal to minus 7.17 plus 12.84x. What does this mean? For every unit change in x, for every unit change in temperature by 1 degree Celsius, the sales will rise by 12.84 thousand rupees for that particular day. So this is huge, because if you see the difference between the sales of first 2 days, the temperature had changed by only 1 degree Celsius and the sales had changed by 2 to 3K. Okay. Whereas on the third day, it's an unnatural or noise. Basically, we can say that the third data point is nothing but a noise. Okay. It's an outlier. So now let's take some validation data and let's calculate the sum of the squared errors. Then we'll also calculate the mean squared error, because sum of squared errors is the sum of all the n errors that you get for all the n data points. So you have to do sum of squared errors divided by n. That will give you the mean square error. Just to revise, 4, 17 means 31 degrees Celsius is the temperature and 17K is the cold coffee sales for that day. This is the equation that we had got for the ordinary least square. We basically will substitute the x values and we'll get the predicted y values. Simple, y hat. And now for each data point, we'll subtract y minus y hat. Okay, and then that error can be positive or negative, so we will square it. We can also take absolute value or modulus, but then that will give you mean absolute error, right? That is also a measure. But the problem is we want to apply calculus further, as I told you, to derive the optimum values for B0 and B1 using calculus. I need, or square basically helps me. So I need something which is differentiable. So y minus y hat squared is differentiable. Mod of y minus y hat could not be differentiable. Another advantage that squaring offers over here is the error gets amplified. So if I just restrict myself to sum of squared errors, that will also be a huge number. As you can see, 1044. It's a huge number. If I take the average of all the errors, so on an average, the error for every data point is on an average 348.07, which is huge error. Now here the units, because we have squared it, the units are 1000 rupees per day squared. Okay, but this is a huge validation error. Just to get an idea of what it means in terms of the validation error per day, we'll calculate root mean square error. So basically we'll take the square root of the mean squared error. So now the units will be back to 1000 rupees per day rather than 1000 rupees per day squared. So when we take the square root, it is 18.65 thousand rupees per day. So that means the predicted value and the actual value on an average roughly differs by 18.65 thousand per day. Okay. Rather, you can say the root mean square error is 18.65 thousand per day. Okay. This is huge. Now, let's discuss the objective function and then I will introduce you the ridge regression. There is a similarity between the objective functions of ordinary least square and ridge regression. Objective function is denoted by j theta, firstly. So, theta is the parameters. In this case, the parameters are B0 and B1 for ordinary least square. We can also use E, L, E for error, L for loss, etc. It can also be called as loss function or error function. But normally it's called objective function and denoted by j. So j of B0 B1 is sum of squared error. So you can say it is summation y minus B0 plus B1x the whole squared. Okay, or y minus y hat squared. So it is easy to calculate partial derivatives and we'll do that in some upcoming video. Now coming to the main point, that is the ridge regression. It adds a penalty parameter lambda and a penalty term lambda b1 square. What does it penalize? It penalizes only the slope. Does it penalize b0? No, it does not penalize b0. Ridge regression penalizes only the slope. It does not penalize the intercept. Only penalty is applied to slope, because slope is what majorly drives the change in y based on changes in x, right? So we have to minimize or penalize steep slope. So squaring b1 square, of course, it helps to nullify in case the slope is negative. Negative sign is nullified, but apart from that, it also amplifies the penalty. So lambda is the penalty factor or parameter, and b1 square, of course, it nullifies negative slope, but more importantly, it also increases the penalty of having a steep slope. And of course, because we have squared it, it is differentiable as compared to using mod, for example. Okay, lambda mod b would not have been differentiable. So this is ridge regression. Actually, the name ridge comes from the way the objective function looks like when it is visualized. Okay, so now let's look at the formulae for B naught and B1 that we get in case of ridge regression. The formula is exactly the same as ordinary least square, except this one additional term in the denominator, that is n lambda. So the slope equation, the equation for the slope, equation for B1 changes only by a factor of n lambda in the denominator. Okay, B naught formula does not change at all. Only the B1 formula changes because of this n lambda additional term in the denominator. So very simple to understand. Ridge regression penalize the slope. Okay, and if you talk in terms of the denominator, so obviously if my denominator becomes larger, then my number will go lower. So b1 will reduce because we have added something in the denominator. So let's say 3 lambda we have added. Why 3? Because n equal to 3 in this case. There are 3 data points, so n equal to 3. In general, it will be n lambda. So because of this n lambda factor in the denominator, b1 will be reduced. It is but obvious because all other numbers are the same. B1 was 44.95 divided by 3.5. That 15 gets added in the denominator, and therefore the slope reduces to 2.43. Huge reduction in slope from 12.84 to 2.43. Now similarly we can calculate the B naught value, and we will get this new equation of the line, okay, which we will call as the ridge regression line. Okay, so B naught value is 11.9122, let's say. So ridge regression line that we get is y hat is equal to 11.9122 plus 2.43x. So this is the ridge regression line. Now let's calculate the validation error using ridge regression. But before that, we'll also calculate for lambda equal to 10. Again, in denominator, you will have 3 multiplied by lambda. So 3 into 10, which is 30. So it is 33.5. Okay. And the slope further reduces to 1.34. If you substitute that in the equation for B naught, the intercept will also change. Intercept changes to 13.9, and therefore the ridge regression line is lambda equal to for lambda equal to 10, it is y hat is equal to 13.9 plus 1.34x. Obviously, as you go on increasing the lambda, when you go on increasing to infinity, the line will eventually become flat. Okay, zero slope, horizontal line. Okay, and the thing is, if you also observe, the intercept also goes on increasing. If you see, the intercept earlier was minus 7.17 and now it is 13.9, right? So intercept is also increasing. Slope is decreasing, but the intercept is increasing. Okay, now let's calculate the validation error as I had told you. That's the point that I want to demonstrate, that how the validation error changes when you use ridge regression, when you use this penalty factor for the slope. Okay, so these are the three values for lambda equal to 5. Similarly, we'll calculate the values for the ridge regression line, the validation error for the ridge regression line for lambda equal to 10. The equation is here on the slide itself. First, okay, so this is the validation error for ridge regression. Now, sum of squared error is 85.37, mean squared error divided by 3, so 28.45. And root mean square error, if you calculate, it will be close to somewhere between 5 to 6, but mostly close to 5. So there is a huge improvement in our model. Okay, root mean square error has reduced. Root mean square error has reduced from 18.65 just to 5 point something. Okay, and similarly, we'll calculate all the values for lambda equal to 10. The improvement will be even more significant. See, because the main driver in case of the predicted values is the slope, and as the slope reduces, the predicted values will stay closer to the actual values. Again, the downside is that if you make it too flat, again the error will increase. Okay, but in that case, there will be training error itself. If you calculate the training error, it will be huge. With whatever we are doing, we are increasing the training error, but we are reducing the validation error. So that is a trade-off that we have. Okay, so it's a further improvement. Now, next, let's consider. Now, here the root mean square error was close to 4.4K. Huge difference, huge improvement compared to 18K that we started with. Now, let's discuss the bias variance trade-off that we had discussed in a previous video on underfitting. We had discussed the variance of the model means a small change in data causes huge change in the model parameter. So that is variance. Okay. Low bias means low training error, and the model is drastically changed when any data point is changed. In simple words, what I want to say is if I change any data point, so for example, the three data point that we had taken in the validation set. Okay, so let's say I change the third point from 2.5 comma 30 to 2.5 comma 26. In fact, let's take the training data, and in training data itself I am changing this slightly, and I'll simply calculate the values and I will show you what the slope I get for ordinary least square. This is using the ordinary least square formula first. So for ordinary least square, change in one data point causes the slope to become. This is a huge difference between the slope that we had originally when the data point was 2.5 comma 30. So 2.5 comma 30 changed to 2.5 comma 26, and the slope has changed by 2 units. Now compare this to the ridge regression with lambda equal to 10. Now in that case, this is the B1 value when the point changes to 2.5 comma 26, and earlier the B1 value that we had already seen was 1.34. So therefore the change is just 0.23. The change in the B1 slope when the data point is changed is just 0.23. So because of this one small change, there was such a huge change in the slope, and you can see that ridge regression is 9.6 times more stable than the ordinary least square regression when the data undergoes any changes, as we saw over here. So that's it. If you have any questions, any doubts, do post them in the comments below. I hope you understood everything. Thanks for watching.